Welcome to Introduction to Quantum Field Theory, Lecture 9. In this lecture, I will set up a relativistic quantum field theory and provide the first steps to solving observables in full quantum field theory. The reference for this lecture is the textbook, Chapter 8. From Lecture 8, please recall that we found that it's possible to write down the Euclidean action for a classical single scalar field phi, and that Euclidean action SE was given by a volume of a Euclidean 4-space d4xe of 1/2 dA phi plus the potential, where A here is a Euclidean index running from 1 to 4. From Lecture 7, recall that once we have a classical action, we can write down the quantum theory partition function through a path integral over all the fields times the exponential of minus the Euclidean action. In addition, we always have to recall that the path integral for the partition function involves a periodicity condition on the thermal circle. So that means that the fields phi evaluated at imaginary time beta are equal to the fields phi evaluated at imaginary time 0 for all values of x. The quantum nature of the partition function is encoded in the infinite dimensional path integral. So knowledge of the classical action provides us full access to the quantum field theory partition function. Unfortunately, not every classical action that we can write down gives rise to a sensible quantum field theory. Also, unfortunately, not every sensible quantum field theory can actually be solved in practice. However, it is possible to solve some quantum field theories, so let's start by looking at those first and calculate the partition function for a fully developed quantum field theory for a free scalar field. So the theory that we want to consider has the particular property that the potential is quadratic in the scalar field phi. In quantum mechanics, we would call this a harmonic oscillator. In quantum field theory, we will call this a free scalar field. So note the difference in nomenclature. Because the potential is quadratic in the field, this will have important consequences. In particular, we will be able to solve that partition function exactly. The fact that the action is quadratic means that we can try to use, again, Fourier transforms, similar to what we did to calculate the quantum mechanical partition function in Lecture 6. The only difference is that in addition to the thermal circle parameterized by imaginary time tau, we now also have to do Fourier transforms with respect to all the other spatial variables, x, y, and z. It is actually convenient to generalize the setup just a little bit. So instead of considering coordinates xi with I running over 1, 2, and 3, I will consider coordinates xi where I runs 1, 2, 3, and so on and so forth up to d spatial dimensions. So I want to work in arbitrary number of spatial dimension, and I write down or denote the number of spatial dimensions that I work in with capital D. Also, I will put the system in a box saying that each direction xi ranges from minus L to plus L over 2, from minus L over 2 to plus L over 2, and eventually I will take the continuum limit L to infinity at the end. In principle, of course, I could consider different volumes for the different spatial directions. This is possible, but tedious to do, so I will not do that at the moment. So now that we've clarified what the size of the system is in each direction, we can write down the Fourier transform. So our field phi that depends on imaginary time tau and the coordinates x vector will be a sum over all these directions. So we have our sum over the Matsubara frequencies n in front. These are the ones that are the conjugate variables to imaginary time. And then we have sums for each spatial direction. So K1 is the Fourier transform of X, K2 is the Fourier transform of Y, and so on and so forth. And all of these just have a usual Fourier transform, a usual exponential that involves the wave vector K in the direction that we Fourier transform. The Matsubara frequencies are again given by 2 pi t times n, and those are dictated from the fact that the thermal circle goes from 0 to beta, where beta is just the inverse temperature. So really what we have is 2 pi over the length of the circle times n. And similarly, each of the ki's that transform the directions that extend from minus L half to L half are basically discretized in units of 2 pi over L, where L is the size of the box in each direction. Once we plug in this form of the scalar field Fourier transform into the action, the kinetic term simplifies. We just get omega n squared plus k squared from the kinetic term. And since our potential is quadratic in the field, we only get an m squared for the potential term that also came as a quadratic form. So the action becomes fairly simple. We have t over L to the power d, which is just the full volume of spacetime that we Fourier transformed in over 2 times this sum over all Fourier components squared times the Fourier coefficients squared. And all of these are summed over the respective Fourier numbers, basically. Since the Euclidean action is in the exponent, and since the Euclidean action is a sum, we have the exponent of a sum. The exponent of a sum is a product, so we can write e to the minus se as a product over the Fourier wave numbers k times the exponential of whatever is left, which is just a sum over these Matsubara frequencies. The main point now is that this exponent here is exactly the same form as the exponent for the quantum mechanical harmonic oscillator in lecture 6, which we solved already. The only difference being there are different numbers appearing in terms of the sum here. So recall that in lecture 6, we found that the action of the harmonic oscillator was given as m harmonic oscillator times t by 2 times the sum of Matsubara frequencies squared plus harmonic oscillator potential squared. Let me just go back one slide. This is exactly the same form here, except that we have different coefficients appearing here. In particular, instead of having m, we now have 1 over the box size L to the power d, so that's just the spatial volume. And instead of having the instead of having the oscillator potential squared, we now have the sum of m squared plus k squared, where k is the wave function, wave vector squared in the different directions. It is customary to use a shorthand notation of the sum of k squared plus m squared as ek squared, because this is essentially something like a kinetic energy term. Once we do these replacements, it's clear that we can just use the result for the harmonic oscillator partition function for this sum over Matsubara frequencies, and we find the result for the full quantum field theory partition function z to be given by the harmonic oscillator partition function, where instead of having the harmonic oscillator potential omega, we now have ek here, and then we have a product over all possible k values. Of course, we can rewrite this in terms of an exponential of a sum of this sine hyperbolic, and it's possible to express the sine hyperbolic as an exponential of this expression here, where basically I've rewritten the exponential of ek beta over 2 in order to find this expression here that involves the logarithm. In the limit where the spatial dimensions become large, so we remove the box, we make the box of infinite size, all of these sums that are over the wave vectors k just become integrals. So in the usual way, 1 over the volume times the sum over the Fourier wave numbers just becomes an integral. So all of these together becomes a d-dimensional integral over wave numbers k with the usual 2 pi measure that follows from the discrete to continuum transition. So if we recognize 1 over LD to be nothing else but the volume of d-dimensional space, this then leads to the following result for the free continuum partition function for quantum field theory. I've written down the logarithm of the free partition function just to get rid of the exponential, and we find by writing LD as v over t times this d-dimensional integral over basically the logarithm of the sine hyperbolic. The problem with this expression, even though it's exact, is that it's badly divergent. You can see that this integral here, if we set, for instance, d is 3, so we think about 3 space dimensions, then we have an integral over k. This ek here goes like this, goes like k for large values of k. So we have something that is the third integral d3k of k that is not a convergent integral. And that's the case for any value of the temperature. This is a standard lesson in quantum field theory. Divergent results are a pretty common feature for quantum field theory. To use quantum field theory as a tool, what we need is a procedure to extract sensible physics that may be hidden beneath those infinities. The procedure that people have come up with involves 2 steps. One of them is regulating the divergence. It's not good to sort of deal with just infinities. We have to sort of see what kind of infinity is. So basically, we want to sort of have some regularization scheme that tells us the precise property of how the expression becomes divergent. And once we have that, we can try to subtract the divergence and see whether something finite and interesting remains once we have subtracted this infinite quantity. The process of subtracting the divergence is called renormalization, because basically we normalize the result by subtracting something we know. For the case at hand, our result for the free partition function in quantum field theory, we can actually understand the origin of the divergence, and that sort of tells us what we have to do in order to properly deal with it. The easiest way to see what's going on is to return to the discretized version of the logarithm of the free partition function. For very low temperatures, the free energy, which is just the logarithm of the free partition function times the temperature, becomes a simple expression where we sum over all the wave vectors of ek over 2. Now this sum is a sum that we've seen before. It is nothing else but a sum over the 0-point energy of all the individual oscillators, where all of them mean that each oscillator is one entry of wave vector k vector, and we are summing over the 0-point energies of all of them. Because in the continuum limit, there's an infinite number of wave vectors that contribute, and we are summing the finite 0-point energy of all of these oscillators, the result for the free energy that we get is divergent. The divergence is just a boring divergence. It just says that, okay, if you sum up the same number an infinite number of times, you get something that's divergent. We already know the physics of the 0-point energy, so there's nothing interesting in this by itself. So what we would like to do is we would like to subtract it out and see if something interesting is there in addition to just an infinite number of 0-point energies stacked on top of each other. there is quite a number of different ways to subtract this, other quotes, boring divergence of the 0-point energies of infinitely many oscillators. A pretty well physically motivated one is the brute force approach of saying that I don't want to sum over all wave vectors k. I want to cut the sum at some maximum value of k, typically denoted by lambda. This cutoff approach basically says that since we don't allow an infinite number of harmonic oscillators to contribute, but just a finite but very, very large number, the sum is not strictly speaking divergent. It's just very, very large, but the largeness is encoded by the power of lambda that appears in the result. So from that point of view, it's very well motivated. The issue, however, with this particular regularization approach is that cutoffs are typically a bad idea if you want to keep Lorentz invariance, special relativity invariance. If you basically use a cutoff scheme that never plays well with special relativity transformations, so it will destroy that symmetry. If it destroys the symmetry, that will have other bad consequences because it will also destroy conserved quantities. This is something we will discuss once we sort of talk more about the Noether theorem and conserved quantities in quantum field theory. So it's possible, it's physically well motivated, but it has the drawback that it is bad if you want to talk about symmetries. A more elegant approach, if we are thinking about continuum quantum field theories, is to exploit what we already started out doing, namely to work in arbitrary spatial dimension D and do something strange, namely that we want to allow ourselves to be working in non-integer dimensions. This approach is known as dimensional regularization, and I will discuss the details of it in the next lecture. The main point being that this approach allows to keep, in particular, Lorentz invariance of the system, but it has interesting consequences that are less physically transparent than just the brute force approach of cutting off the sum and putting a finite cutoff lambda there. And we'll talk about what that means in the next lecture. This concludes the present lecture.